This presentation is about conditional distribution and conditional density. So we have two random variable x and y on a probability space. Now conditional distribution refers to probabilities which are of the form probability y belongs to b given x in A. Now you know that you know the definition of conditional probability, right? For any two events b and a, probability of b given a is probability of a intersection b divided by probability of a. So by that definition, this will be equal to probability that xy is in a cross b divided by probability of x in a. Of course, this is defined provided probability x in a has a positive probability. So that is the conditional probability. And so next what we will do is that we will define conditional distribution and conditional density for random variables which have joint density and joint mass function. So suppose x and y are two random variables with a joint PDF f. So I have given you an exercise example that suppose fxy is equal to x plus y. So you see that for xy in between 0 to 1 and fxy 0 otherwise. Zero otherwise. So I leave this as an exercise for you to verify that this is a density function. Obviously this is non-negative valued and you have to integrate over the two variables x and y with respect to 0 and 1. So if you integrate with respect to x and y, so you have to verify that it adds up to 1. So then the exercise is that you have to compute the, suppose xy is a joint density, and so xy is a two-dimensional random variable with joint density f. This f that I have defined of f defined above. So then you have to calculate these probabilities. So probability that y is less than 1/3 given x is bigger than half. So suppose I am measuring the variable x first. So I have found from the data x values I am looking at only those which are greater than half. And then I am looking at the y coordinate. So I want so first x is observed, then y is observed. So you can think of this like this, that suppose x represents the height and y represents the weight. Now suppose you are interested in candidates who are above a certain minimum height. For instance, in army recruitment, so not all the applicants are considered, so they have to satisfy some physical criteria. So suppose only those male candidates above a certain height will be considered for further. So here suppose x is x and y I am not considering to be heights because they are between 0 and 1. So suppose they represent some parameters. So we are interested only those values of xy where x is more than half. So then the condition, then other values don't make sense. So I would be interested only about probability statements about y where x satisfies this condition. So then by this definition, this will be the joint probability that x is more than half, and I had told you earlier comma stands actually for the intersection, and y is less than 3 divided by probability x less than half. Now we know that how to compute this joint probability. So joint probabilities you obtain by integrating the joint density. So the formula for joint density is given here. So both x and y are taking this density is taking non-negative value for xy in the inside the unit rectangle. So along x-axis 0 to 1, y-axis 0 to 1. So you have this points xy in the unit rectangle on the xy plane. So for there it is the value x plus y 0 otherwise. So y less than 3 means it will be 0 to 1 by 3, and x more than half means it cannot be above 1. So you have to integrate and find out the value here. Now to compute probability x greater than half, you need the marginal density, because you integrate the marginal density to get the marginal probabilities. So marginal density you obtain by integrating this function joint density, but keeping x as it is, but integrating over the other variable y. So when you integrate, it is x plus half between 0 to 1. So now you obtain probability x greater than half by integrating this marginal density function over the desired range. So half to 1. Why? Because again this function is actually this function is x plus half for x between 0 to 1, and I have not written here because it is implicitly understood, and this will be what, and this will be equal to 0 otherwise. Why this will be 0? Because if for any value of x less than 0 or above 1, this function, the integrand is 0, no? So therefore we have the marginal density also defined on the interval 0 1, and it is like this. So x greater than half means essentially integrate from half to 1. So once you have done this, you have solved this problem, because now you can just take the ratio of this probability defined by the last probability that you have computed, and that ratio will give you the conditional probability. Now, analogous to the concept of conditional probability, I can define conditional density. So for any point x for which fxx is positive, I can define a function, new function, which is the ratio of the joint density fxy divided by the marginal density x. So now I am leaving as an exercise to verify that this ratio, new ratio that I have defined and which I am calling by the name fy given x equal to x. So this is the density function. So for that you need to verify two things. So first is that this is non-negative value, which that is obvious, because it is the ratio of two densities, that is two non-negative valued function, and if that integrates to 1, so that is also no big deal, because you have to integrate with respect to y to 1. So here the variable is y, x is fixed. So when you take integral over y, this is the denominator is a constant, it comes out. What is integral over y fx dx? That is exactly the definition of fxx. So therefore the ratio is 1. So you see, now this ratio turns out to be a non-negative value and it integrates to 1. So it is a density function. And since it is computed for every fixed value of x, so I am denoting it by the symbol y given x equal to x. Now this is called, I am giving it a name, important. I am just giving it a name. This is called the conditional distribution of y given x equal to x. Now here is an important disclaimer that one should always remember when looking at these functions, that you know that for any function, you know that the conditional probability of a given b is defined as the ratio of probability of A intersection B divided by probability of B. So similar to this, but it makes sense only when probability B is defined. But but this conditional density that you have defined is not a conditional probability in this sense. Why? Because since x has a density, means x is a continuous random variable, and for continuous random variable, you know probability x equal to x is 0. So for any continuous random variable, these kind of probabilities, that probability y given b given x equal to x, is not defined in this sense. Rather, this denotes a probability obtained by integrating over this function that you have defined. So this will be So this is a probability that I am obtaining by integrating this new density that I have defined, which I am calling the conditional density, of y given x equal to x. So the probabilities like these are called the conditional distribution of y given x equal to x. So this conditional distribution of y given x equal to x is not exactly the conditional probability for continuous random variables, because in that case this probability x equal to x doesn't make sense. But anyhow, you can always compute probability by integrating a density function. So when you see, so in the next exercise I have given you the same problem, that compute the probability y less than 1 by 3 given x equal to half. So in exercise 1, if you go back, so here x and y are continuous random variables with joint density this. So you have also obtained the marginal density. So if x is continuous, that means a probability x equal to half is 0. So as such, this conditional probability doesn't make any sense. But now you know how to compute this. So you have to first get the conditional density x y given x equal to half. Yeah, A2 law of karone you have to find out f y given x equal to half. So once you have found that out, tar mane A2 keneke ulabo, that will be the ratio x plus y divided by x plus half for x between 0 and 1 and 0 elsewhere. That will be the formula for this, and there you put x equal to half, and then you have to integrate y over the desired range. So I hope this is clear. So and finally we have this chain rule. Chain rule mane ki, look at the formula for joint conditional density. So from here we have fxy, the joint density is the product of the marginal and the conditional density. So this rule is similar to the formula that probability of A intersection B, this A, if you recall, intersection B, what was it? That was equal to probability of B given A into probability of A, provided probability of A is positive. So it is similar to that, but this is not exactly the same thing, because these are not probabilities. Y given x equal to x is not probability, is just another non-negative valued function which integrates to 1. Okay. So I will give in exercise, I may give you an example. I may give you joint densities like this with some different formula, where I will ask you to compute the marginal or the conditional probabilities like this, or any combination of them. So please practice them.